Thank you all for joining us today. Our speaker for the day is Nicholas Soros. Nicholas is a PhD student in the Neuromorphic AI lab, and I've been working with him for the past 5 years. He has done his undergrad from SUNY Binghamton in physics, and for his master's and PhD, he decided to see how he can apply the knowledge he's learned in the physics to engineering. So he has chosen computer engineering, and then from there on, he started, I guess, exploring a lot of neuromorphic systems and architectures, and got really interested in addressing this problem of continual learning and how you can use biology as a source of inspiration to solve problems of continual learning. He's going to explain some of the work he has been doing for his PhD. And I guess this is a recent publication in the ICML workshop, and that has received a lot of attention in how to solve continual learning using these, using combination of mechanisms that he has found in biology. So this is a first presentation by a student in the Matrix AI seminar series. And I thought this would be a good flavor for some of you who are considering PhD, or some of you who are already doing PhD, in how your research contributions can be impactful, at the same time, how you formulate a problem and how you take it to designing a solution for those problems. Thank you, Nick, for stepping up in the last minute and giving this talk.
No problem. As you might be able to notice by now, is I tried to change the format of the title slide, so the title is kind of wrong, which I just caught on. But yeah.
The floor is yours, Nick. You can go ahead with
Okay, thank you. So what I'm presenting that is almost the same as what this title says. So the focus is on task agnostic continual learning, or TACOs, in spiking neural networks. And so, you know, my title right now is just neuroplasticity for continual learning and spiking neural networks. So both mean the same thing. But if you see a discrepancy with the information that was shared and the title presented here, that's just why. There we go. So I'll quickly introduce the lifelong learning and the problems that I'm looking at before I get into kind of some relevant background work, which involve neurally inspired mechanisms for the brain, and specifically, you know, what plasticity mechanisms that I'm focusing on, and how and why I think integrating them can be a good solution for continual learning, specifically in spiking neural networks. And then I'll kind of introduce to you guys my proposed TACO model, which we presented at the ICML workshop last year, and go over some of the results that we presented there. So in general, you know, lifelong learning systems are systems that want to rapidly adapt to new conditions or to new tasks throughout their lifetime. You know, so you might have something trained to perform one task, such as in a figure like a sport like golf, and then, you know, you learn something like weightlifting, right? And you don't want to forget how to play golf. You don't want to start treating the club like it's a barbell or something like that. You need it to remember, you know, different tasks, how to use those tools for different tasks, and what the goals of those different tasks were. And even going beyond that, you know, we think that rather than just learning task 1 and task 2 and treating it as a traditional AI model that learn that individual task and processes that task separately, you can kind of pool information between tasks to improve your performance on both. So the end goal is something more like we see in this bottom plot, where your lifelong learning system's performance is continually increasing over time as it learns new tasks. Sure, there will be some drops periodically when you experience a new task and it takes some time to adjust. And minimizing those gaps or those drops is an important part, but the goal is to just continuously, you know, acquire and accumulate new skills and learn how to use those skills to solve new tasks and do better on previously seen tasks. you know. So kind of a more formal definition for a constrained problem that we can study is that we can think of a distribution of tasks D, which consists of n number of tasks, T1 to Tn, and each task consists of, a data and label pairs. Our goal is to minimize, the overall loss or the performance, or to maximize performance on every task seen throughout the agent's lifetime. It sounds kind of simple, but it's not. That's not a very inclusive goal. So you can minimize loss in a lot of different ways, and there's a lot of trade-offs. So there's things like forwards transfer, backwards transfer that we talk about, where it's, does that result give you good performance on old tasks, or is it just, does it improve performance on old tasks, or does it just kind of retain their previous state and reduce learning on future tasks? So you can get into a lot more details. Specifically, what this work focuses on are constraints that are added to that goal when we consider real world deployment. So for us, we think about mitigating catastrophic forgetting under realistic conditions where, you want a system that can learn with things like constant memory, that can learn from streaming online information, where it's only going to be able to see samples once and experience that in real time and have to update to it and then not see it again. It's not going to have access to task knowledge, so it won't know currently which kind of a problem it's trying to solve. Provide as an oracle outside of label information. So there's no predefined task boundaries or test time oracles during inference. And then there's additional challenges that would come up, which involve, data movement, memory capacity, and all that kind of stuff. So some of the energy results and the computational results, those won't be in this talk. They were done for a later work, and they involve a bit more than what's going to be presented here, so they wouldn't make complete sense to show. But we'll talk about how the proposed approach addresses, just learning from a single sample, single epoch, basically, and how it's task agnostic and doesn't grow over time. So some of a quick recap of neurally inspired mechanisms for lifelong learning. I can kind of group these into three broad groups. The field is continually growing and people are proposing new models. But so the first one that I'll talk about is dynamic architectures, which is approaches that usually involve some form of either selecting a subset of neural resources to use, which is like context-dependent gating, or some form of structural plasticity, where you're growing or removing neurons and synapses over time. So you're changing the architecture of the network as needed while learning new tasks. So these approaches, they work well because they can add new resources to kind of take control of the learning process when experiencing new tasks. And that way you don't have catastrophic forgetting in prior neurons that learned old information. This is very similar to adult neurogenesis that goes on in the human brain. But the downsides to this are that, typically most approaches will require task knowledge or meta learning. If they don't, then usually they'll suffer from another problem that regularization approaches or plasticity approaches will have, where you can't do something called class incremental, which I'm not going to get into here. But they can be restricted to learning inter-task boundaries, is the long story short. Or the other downside is that dynamic architectures can grow unbounded. So for plasticity, I don't have a little figure here. We're going to talk more in detail about this one because this is what TACO's focuses on. But this involves things like synaptic consolidation, metaplasticity, and local learning, in the brain-inspired space. And it also involves, more than that, regularization approaches, which try to, retain information while learning new tasks. And they do this by either, preventing weight changes to important weights, which is similar to what metaplasticity does, and synaptic consolidation, or they do this through approaches trying to regularize the network's activity so that your layers produce the same outputs to previous responses as they used to, even if the weights are changing, as long as the representation created by that layer is the same, you kind of achieved your goal of responding the same to old inputs without forgetting, you know, kind of how you respond to that input. So these methods are, you know, nice. They kind of just integrate with the learning that's already going on in the network without too much overhead. But the issue is, you know, you need to protect information by knowing what information is worth protecting. And some methods to determine that can be expensive, such as using Fisher information or gradient information. And they can also, you know, eventually they'll reach a point where they reduce learning on future tasks, because now so many of your synapses are protected or frozen and prevented from learning that you can't learn the newest task. So you might retain some form of accuracy, but you don't do well later on, and you kind of stop learning. And then finally, the last play, and probably, you know, the highest performing method, though it's a little bit different than the other two, is replay or rehearsal. And so, you know, this approach is where you're kind of saying, you know, we've seen X amount of past tasks, and we have some way of either storing data from these tasks or generating data, you know, similar to what we experienced during that task. And then we can retrain the network with that, you know, stored or generated data. So, you know, it's nice because it directly allows your network to continue to retrain on all the tasks seen at once. So instead of these, you know, changing data distributions or changing tasks, it kind of tries to solve it all at once as a traditional AI problem. I mean, not to the same extent as a model would, because you have limited data samples from both sides or synthetic samples. But what this requires is, you know, an offline learning phase where you can kind of disconnect your model from whatever it's doing in the real world to kind of train on some batch sample of replayed or rehearsed data. It can have memory limits with buffer-based approaches where you can't, you know, store an indefinite number of memories. Generative models kind of address this issue, but then they get into their own issues too. So each approach, you know, you can pick pros and cons for, and there's works addressing all sorts of different issues and creating more issues. So it's a very fast growing and changing field. But specifically, you know, I'm going to kind of focus on some of the plasticity approaches and, you know, how they relate to what I want to do, or what I've observed, you know, from kind of looking at continual learning from the biological side and how I adapted that to my spiking neural networks. So, you know, there's kind of three approaches that generally summarize what you can kind of do with plasticity. So the first is regularization. You know, the idea is that, you know, when you transfer, you learn some information in task one, and when you go to task two, a subset of your synapses have gone through some metaplastic change where, you know, plasticity at those synapses will now be restricted. And that can be, you know, a restriction at the neuron level or the synapse level. And it can even be more, you know, broader than that, you know, layer wise, etc. Transfer learning, you know, this is where you pre-train a model and then you kind of just freeze its synapses and then use that as a representation or some form of information to boost your performance on later tasks. This one, you know, is not as common by itself unless you're pre-training on some third-party data set that doesn't belong to the current problem, or if you're trying to freeze a subset of the network and then either instantiate new resources around that through something like neurogenesis or other approaches. And then the final kind of related to plasticity in the network is local learning. And so one thing, you know, that we observe with backpropagation, and even with, you know, attempts to mimic backpropagation and spiking neural networks, is that you kind of update all your weights in response to an error. I mean, there are ways that don't get updated when gradients are 0 or your presynaptic input is 0, but in general, you're saying, okay, let me try to update this synapse. Whereas with, Hebbian-like learning, it's much more restricted. Updates are much sparser, and you get less catastrophic interference than when you use some kind of backpropagation-based approach. And this is what drove most of the early continual learning works in spiking neural networks. So they're all based on Hebbian-based learning rules that work with just a single layer, but kind of inherently avoid catastrophic forgetting with just Hebbian learning and other intrinsic plasticity mechanisms to drive learning to different neurons at different times. And it's great and it's interesting. The hard part is that Hebbian learning can be limited to a single layer. You can't incorporate, or you can't get the performance you get with backpropagation just trying to use Hebbian learning. And the problems that backpropagation suffers from are also experienced by surrogate and gradient methods for spiking neural networks. And I'll talk about one of those later that we use in tacos and why it suffers. And so we need other approaches to kind of mitigate this. And so the first part that I look at is metaplasticity, where the idea, is that you induce a metaplastic change to a synapse so that when potentiating events occur, the changes to that synapse are kind of reduced or prevented. So in this figure, we have a synapse, and in the blue we see its response to a nerve impulse that it receives, right? So after depotentiating event occurs and you have a similar nerve impulse, the response is much lower, right? The increase in memory potential is reduced. But if there's a metaplastic change to that synapse and it undergoes a depotentiating event, then the next time it sees that identical pulse, even though it had a depotentiating event, the response is identical. So metaplastic, stabilization can kind of help keep a synapse, help a synapse to maintain its knowledge or information when being, when undergoing potentiating events driven by backpropagation or the surrogate gradient learning rules for that current task. The second kind of mechanism that I started looking into and considering was synaptic consolidation. And this one is kind of discussing the transition of short-term memories to long-term memories. So synaptic consolidation is a form of long-term plasticity where you'll induce some changes through weak stimulation, which will cause some physical change in the synapse, which we represent in a neural network as the synaptic strength. But that in early phase LTP, that strength will decay back. You'll learn something and then it kind of starts to decay because you'll say, okay, I don't know if this was necessary. This is just right now, this was what my update rule set to do, but I don't know if it's, a one-time event, if it's noise, if it's, kind of an outlier, etc. But over repeated stimulus or strong stimulation, you'll kind of maintain and consolidate that information, and it won't decay. So it'll become a permanent change to the synapse. So by combining these, we get kind of a much better performance at continual learning than either one by themselves. And we'll show that with more specific values later. But at the high level, the thought process driving this approach in our mind was, how do these mechanisms cooperate and why are they needed? Why can't we just do one or the other? And so, what our hypothesis was that metaplasticity is going to restrict the updates of important synapses. We saw how, in the figure, after a metaplastic change, changes to a synapse are weakened or reduced. And so what this will do is, you'll learn a task and then, let's say task 1, and you reach some fixed accuracy value for task 1. So when you go on to learn task 2, a lot of your important synapses for task 1 will be prevented from changing, and your performance will drop only slightly. Whereas if you have no metaplasticity, just doing task-driven learning, your performance will drop very quickly, maybe back to where it was before, unless there's some sort of shared information between the tasks. But it has no way to recover from those changes, right? So once your performance drops, unless you train on task 1 again, your performance isn't going to go back up. Synaptic consolidation, on the other hand, it's going to capture information over a longer time scale, which will kind of prevent, your network from unlearning task 1 as fast. So if we see in consolidation, the rate that it drops while learning task 2 is less than if there was no consolidation because of that decay factor, but it's still much faster than metaplasticity. But unlike metaplasticity, it can allow some of those weights that change during task 2 but haven't fully consolidated to return back to their previous states. And you kind of regain some of your performance on task 1 because you're returning to an older state where you did better on task 1. So by combining these two, you kind of get the best of both worlds. You reduce the changes in the important weights, and you allow the network to recover from gradual shifts that are unavoidable, even with metaplasticity, unless the synapse is completely frozen. But you also don't want to completely start freezing synapses, because then your network really becomes untrainable. And the goal is to find a balance between this kind of regularization and this plasticity that's allowed, so that we can still learn future tasks. But so, I'll get into the proposed model, more of the details now. I'll talk about how we train it with surrogate gradient neural networks, just for those who aren't familiar with spiking neural networks, or, how we're applying a mimic of back propagation to them. I'll show the specific metaplasticity and synaptic consolidation functions in terms of the network, and then some of the results. So, again, what my title was originally going to be was Task Agnostic Continual Learning and Spiking Neural Network, or TACOs for short. And as Dr. Pudipudi mentioned earlier, we presented this at ICML workshop for the theory and foundations of continual learning. So, as I was saying, the key points are using heterogeneous neuroplasticity to aid in designing continual learning systems, again, with the goal of being energy efficient, which I'm sorry to say is not in this presentation, but that is an important focus of this work. So we wanted to look at, local plasticity, removing task knowledge, sparse updates, low communication overhead, binary spikes, etc. Utilizing complex synapses. So we have heterosynaptic decay, metaplasticity, consolidation, and their role when working together to mitigate catastrophic interference rather than just by themselves. And that these models don't grow as a function of the number of tasks. So yes, there's overhead when you're introducing these multiplasticity mechanisms, but it's not growing, which is important, because many models, you're going to be needing to add resources over time. And that's something we want to avoid. And then, we like spiking neural networks because of those, how easily they can integrate with some of these bio-inspired rules, because they have energy efficiency in communicating with single spikes that are binary. And this kind of just reiterates that point. But I wanted to show kind of a graphic of what a spiking neuron is for those who might not be as familiar. So what this model is doing is we're replacing all the neurons in the network with, that might be ReLU or sigmoid or TANH, something along those lines, with these spiking neurons. So, you have a temporal neuron that is now integrating binary information over time. So you have incoming presynaptic spikes, which are these blue pulses. And every time your neuron receives a blue pulse, its membrane potential increases. And once that potential reaches a threshold, your neuron emits a spike or a red pulse. So you can think of these neurons as communicating with binary information, 1 or 0 at time step t, which indicates whether they have fired or not. And, you know, this is nice because you can take advantage of this sparse spiking activity distributed over time to kind of reduce the updates overall to the network. And that's kind of like how heavy learning does it. It looks for correlation between, you know, spike activities local in a very small time window, rather than just saying, you know, during this sample, which neurons were active, train all of those neurons. And it also doesn't, you can also not allow neurons that did not fire to still learn, right? But that's a kind of a double-edged sword or whatever, because, you know, if you say a neuron didn't fire and you want to protect it from changing its information, which backpropagation would have done, sure, you prevent a change from something that might be important to previous tasks, but you're also greatly restricting the solutions that your network can find and learn. But so you get this interesting balance where you can, you know, mix in these local plasticity learning rules with backpropagation inspired learning and spiking neural networks. And then again, you know, just neuromorphic, the goal is energy efficient systems. You can get cheap spikes with 20 picojoules per spike. You know, binary spikes are very robust to noise. They don't involve multiplication operations when you do your neural network operation, because it's just a binary value. So, you know, if a spike is there, you accumulate whatever that synaptic value is, depending on how realistic the model is. But at the simplest level, that's as cheap as we can get with, you know, some of these abstractions. So I'll just talk a little bit about the surrogate gradient learning. So the way you learn a specific task or mimic backpropagation is through something proposed by another group called event-driven random backpropagation. And the idea is that, you know, we can mimic backpropagation in the brain, but there's two issues. The first is that, you know, synapses are not bidirectional, you know, transposes of their forward weights. So we have a different kind of random set of weights that are feeding error information back to the network. And the second is that a spike, you know, when it goes from 0 to 1 is a non-differentiable function. So we need some way, you know, some surrogate to approximate that gradient. And their learning rule became very simple, and I'm probably not going to spend too much time discussing the next few slides, so I'll try to just sum it up. But essentially, you know, if a postsynaptic neuron has fired, oh, sorry, that should say presynaptic neuron. Oops. So if a presynaptic neuron has fired, and the postsynaptic current is within some range, then you can update that specific weight, right? So you have the synapse connecting your presynaptic and postsynaptic neuron, and if those two conditions are met, your weight is updated. And that's a very Hebbian-like rule. You have some presynaptic condition and some postsynaptic condition, which are typically just if both neurons have fired at that time step or within a certain window. But you know, we need to add some form of error information to that update, right? And so ERBP does this by accumulating error in a second compartment of all the neurons in the model. This error is accumulated through random feedback. So, you know, your backwards weights are just random values, but still based on your error between your output layer and your target output pattern. So, you know, so your hidden layer, you know, for those interested, these are the specific equations for updating both the synaptic current and then the neuron membrane potentials, as well as their error compartments. So I'll just quickly focus on, you know, your V, which is your membrane potential, is integrating feed forward information, whereas your U is integrating, you know, your error information, which is, you know, your SEs that you see. So SE represents, you know, if your error neuron spiked. So if a target and output neuron output don't match, it will induce a spike in your error neurons. And then that will get fed back through some random weight to your hidden layer. And you'll just accumulate that information over time. And when a synaptic update occurs, you will modulate the synaptic update based on that accumulated error. The same thing happens at the output layer, except instead of random feedback, it's one-to-one, because you only want to change that specific output neuron with the error that it's inducing. But that's the gist of how the weights are being updated. A minor detail, it's not really minor, but it is for the purpose of this talk, is that we have two different sets of error encoding neurons because we can't encode the negative values in the spike trains. I mean, not when we're being realistic. So there's two sets of neurons. One is for false positives, which is when a spike, your output neuron Y spikes when it shouldn't have, and the other's for false negatives. An output neuron spikes or does not spike when it should have according to your target spike train. And together, both of these are fed back to your network to tell it what kind of error it's making and how to train. And so this does very well, and it can get very close to backpropagation results. And I'll show later, using this learning rule with the spiking neural network, we can get state-of-the-art or near state-of-the-art results on some common continual learning benchmarks. So to get into each of the plasticity mechanisms now that we're going to use to control that surrogate gradient learning for continual learning, I'll start with metaplasticity and then I'll discuss consolidation. And so, as we said earlier, metaplasticity is the plasticity of plasticity. Basically you are regulating how much a synapse can change in response to, some kind of error signal that it's received during its normal weight update. So our goal, is to just reduce the synaptic plasticity based on a neuron's importance. And I mentioned this earlier that, we can estimate importance using a variety of information. But often, we need to know when a task is over so that we can know which, all the information about the network during that task, about the gradients or about the network responses, and compute different forms of metrics to measure importance. Whereas our goal is to, estimate importance on a line, to not store this information over time, and to not know when task changes have occurred. So somehow we need to estimate that importance, and we need to show or reflect that importance in a neuron's metaplastic state. So to do this, we found another group that applied a global metaplasticity function where your metaplasticity is this exponent of the negative absolute value of your metaplastic state times your weight, where that metaplastic state was a global value applied to the whole network. So the idea was that as your synaptic strength changes, your plasticity changes, right? So now you have no need to estimate your importance. Your importance is given by your weight value. So the larger your weight, the more important that synapse must be, and therefore we're going to reduce the learning of that synapse. This works. It worked well for them, and it works in our model too, but we'll show that later on. It's not as ideal as being able to kind of dynamically estimate importance and starting from smaller metaplastic states. So what we did was we said, well, how about we have a way where we can change this M value? Instead of a global value applied to the network, we can now increase M every time, that synapse's pre and postsynaptic neuron is active enough during a sample. So, so as long as both neurons fired frequently to that sample, then that synapse was conveying some form of important information that was needed for that task or was used, and we're going to want to protect what it has learned during this given time. And the increment to that metaplastic state will be small. But over time, we'll start to get a representation of which neurons have learned recently, or which synapses have learned something new recently and have been contributing to what we've been learning and need to be protected. So this way, we'll have faster learning earlier on, and we can achieve a much higher state of protecting information than we could if we just used a global parameter off the get-go. The second form, or the second approach, the second plasticity mechanism is synaptic consolidation that we talked about. So again, we're trying to, consolidate information over a longer period of time, allowing plasticity induced by the surrogate gradient learning rule to kind of decay unless the network determines that, it's important enough to be maintained and transition to long-term knowledge. So the way we do this, we have a fast component, which we can consider as your traditional weight in a neural network. So, this learning rule looks all fancy, but this is just basically saying back propagation for spiking neural networks. So your fast weight is updated akin to how you would update your weight with back propagation. So now what we want to do is we want to also give the network kind of a slow component, which can balance the current task knowledge with previously learned knowledge. And so this slow component, which I'll call a reference weight, or WREF, is, trying to slowly approach that fast weight's value over time. So what this does is it now allows the slow component to integrate that information. So your fast weight might change up and down, and the slow weight will be kind of some moving average reflecting those changes over time. But that's not enough by itself. We also need some way to allow the slow component to affect the changes to the fast weight, or to your regular weight that's used for inference. And this is where the remembering comes from. So the slow component is giving you kind of a sense of where was I previously, but now we need to say, okay, if this is where I was before and this is where I am now, I want to go back there at least a little bit. And we do that through heterosynaptic weight decay. And what this does is, your fast component is just forced to decay back towards its previous values anytime its postsynaptic neuron emits a spike. The goal of this, is to form some kind of balance between slowly consolidating your new information while at the same time preventing changes from your past state, which were important to prior tasks. So by combining all of these together, we have the complete tacos network. So you have your ERBP, event-driven random back propagation, driving your learning to your output and hidden layers, and your synapses are, undergoing plasticity driven by this kind of surrogate gradient learning rule, but protected now by both your activity-dependent metaplastic state and your reference weight of synaptic consolidation. And so the combination of these mechanisms allow tacos to kind of achieve state-of-the-art on simple visual domain incremental learning tasks. So what we tested this on was split FMNIST and SPLIT-MNIST, and I think I deleted the visual slide showing the different tasks by accident. That's why I was confused for a minute. I was going to explain what the tasks were a little bit better, but you'll have to just try to follow my voice, I guess. So the idea is that, let's just take MNIST, you have the digits 0 through 9. So the first task is classifying if the digit is a 0 or if it's a 1. Then the second task will be classifying if it's the digit 2 or the digit 3, and so on and so forth. So you have 5 tasks: 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9. So your whole time, your network only has 2 output neurons, and it's just trying to tell you whether it was pattern 1 or pattern B, which actually turns into, is it odd number or even number every time it's presented. This kind of approach is called domain incremental learning, where your output layer is shared across tasks, but the network doesn't have to know when it's classifying which task it belongs to. It just has to know if it was one of the numbers from the first set of patterns or one of the numbers belong to the second set of patterns, but it's only trained on one set at a time. This is the common approach used for regularization approaches because they can't learn intertask boundaries necessary for more complex tasks where you have to say, you know, which number is it specifically even learned over time. So, you know, you learn 0, 1, then you learn 2, 3, and you have to be able to tell you, is it 0, 1, 2, or 3, instead of is it just 0, 1, or is it 2 or 3? So that approach is a bit more challenging for regularization approaches, where actually all of the approaches in this table get basically random guessing at that approach. They get 20%, including ours at the time. That's kind of some newer research that we're working on, is how to address that problem. But anyways, okay, so we're digressing. So the important thing to focus on, you know, in these results is twofold. First is that we compare the baseline spiking neural network with just metaplasticity. You know, what do you do when you just add consolidation, and then the proposed approach tacos. And you can see, you know, a very significantly large increase in performance from tacos, whereas just metaplasticity by itself or just consolidation by itself, no matter how we swept those parameters, couldn't get that same improvement in performance, especially in the MNIST case. The second important point is that tacos is outperforming all of the other approaches when it was only trained with a single epoch of information and does not need any form of task information. So, you know, the second closest result is stochastic synapses, which is reflected by SS in the table. And so they get very, you know, similar accuracy values. And one important thing to note, though, is that they actually have less memory overhead than tacos does. So they're you know, one of the lowest you can get when considering the regularization-based approaches. But other than them, tacos has, you know, a much lower memory overhead compared to the third best state-of-the-art method. Whereas when looking at the rest of the groups, they're either rely on task information or their performance is very poor. You know, so when just looking at kind of the top 3 performers, we're near the lower end of the memory overhead, but we're getting that great performance while only training on a single epoch. Whereas, you know, the other approaches, definitely stochastic synapses was trained for 5 to 10 epochs. I forgot the specific value. And BGD was trained for more. But so those are kind of the main points when comparing tacos to just simple SNN and tacos to relevant state-of-the-art approaches. When we want to look at tacos specifically by itself, you know, we want to consider 2 things. One, how does this model perform in comparison to the baseline approach in terms of not just, you know, retaining information, but also learning downstream information. Because if we remember in the beginning, I talked about, you know, sure, we look at this final value mean accuracy as the end all be all for continual learning, but there's a lot more aspects involved about, you know, are we retaining information, you know, and just not learning new stuff? Are we kind of learning new stuff and forgetting? Are we learning and improving our overall performance? It's important to understand how it's working and how these different approaches work when you're trying to compare them. And we also wanted to look at, you know, how do we do compared to that fixed metaplastic state where you just estimate importance based on weight magnitude? Because again, one of our points was that we want to be energy efficient. And if we can remove that overhead from that dynamic metaplasticity, it's important to know that. I see there was a hand raised. I don't know if there were other hand raised earlier.
Oh, hi. This is Gabriela Chocotlia. So I have a question. So the results that we have here are on a particular type of application. I'm wondering what other applications have you used with tacos?
So yeah,
aside from image classification, thank you.
Yeah, None, actually, sadly. So what I'm trying to do, I started trying to look at reinforcement learning with surrogate and gradient models for spiky neural networks. But I haven't got anywhere beyond just playing cart pole with the network yet. I'm kind of new to reinforcement learning and spiky neural networks. And then the other tests that I'm looking at are all visual based. So I've been looking at using CIFAR 10, CIFAR 100, and using a few more grayscale data sets similar to OmniGlot and MNIST like images from other groups. So yeah, so nothing yet beyond kind of the visual domain and specifically grayscale images.
Got it. Thank
Sorry.
you. I'm looking forward to seeing the next round of applications. Thank you.
I am too. Yeah, I hope to have something more convincing too, and just show its use, show its benefits better than this. But these are, MNIST is just so convenient for, you know, testing basic functions and comparing. So that was the first round's focus. But yeah, so what I was saying was we wanted to compare it to the fixed metaplastic state to show that, you know, even though it's a little bit more expensive to have this dynamic metaplasticity in terms of parameter overhead and computations, it's necessary to get better learning and better retention overall. And the reason being, you know, so tacos, let's say, can get up to a metaplastic state of 25, where, you know, we'll just say you have very restricted plasticity. If you start your network from that state of 25, you have almost no ability to learn, whereas tacos can only grow to that state once that synapse has learned a significant amount of information. So this way, you know, we can get to this point where it's near frozen only after it's already been trained on something important. And then, you know, the question becomes, you know, did it have time to learn everything it could, or did it take too long? You know, did it learn task 1, then task 2, then task 3, then it became frozen, right? And so there's a lot of balances. And what we can see from this plot, you know, is in comparison to this baseline model, which is this gray dot, on every single task, when we learn that task on the dashed line, the gray dot is always the winner in future tasks. And we can see that, you know, as the metaplasticity value becomes higher, our specific task accuracy becomes lower and lower. And so we can see that, you know, even early on for task 2, we start to get some form of punishment in the terms of degradation and learning future tasks. But typically for, you know, the same maximum metaplastic state, tacos suffers less, and it allows for more plasticity. And we kind of, every time I click a different screen, there we go. As we kind of also show the same result by looking at the average plasticity of the weights. Again, we were trying to just compare, you know, is this dynamic approach worth it? How much more plasticity does it allow? And how much plasticity does it not allow in relation to a baseline spiky neural network with nothing? So we can see, you know, A, you know, why is it better than prior work? And then B, you know, how much are we still sacrificing with this approach? And then consider later how to fix that. But so as we can see, you know, all of the tacos approaches, even with very high metaplastic values, show a much larger plasticity in both the input and the output weights when compared to a fixed approach. Whereas when compared to your SNN though, you know, so the best performing tacos is around metaplasticity equals 25. We can see that, you know, we have almost 3 times less plasticity. Specifically, you know, I mean, the output layer, you know, overall change at the end is kind of similar, but the last task change is pretty similar, but the overall plasticity in blue, which is all the changes in weights since task 1, is, you know, almost 3 times bigger when you use tacos versus, or in an SNN versus when tacos is included into that model. And that results pretty, you know, equivalent in the hidden layer. So we see that there's this, you know, large degree of plasticity, but, you know, again, at the same time, we can measure, how much information we retain because of that loss in performance. And so we do this by just comparing hidden pattern or the hidden layer representations when it was trained on a task versus when it was trained for all tasks. So specifically, we just report here your task one's cosine similarities of what the network representation was when learning task one versus what your network representation was after learning all tasks. And, so we can see again, where tacos is m equals 25. Sure, the cosine similarities are a bit, actually, no, only pattern 0 is a little bit lower than the fixed metaplasticity. But it's important to note that, this fixed metaplastic parameter, especially here, basically doesn't learn anything useful. So even though your pattern changed less, it never learned a meaningful pattern. So it's a little misleading there, but we can see that, it's still a much higher similarity than your SNN model, especially when considering the digit 1, where we, the cosine similarity dropped by like 0.13% or 0.12%, almost 12.5. So that was just some different ways of viewing, how much knowledge is retained in tacos versus, other approaches and how much we restrict plasticity. So here's the slide that I told you guys about earlier for data sets. I guess I have this all in here twice. We're not going to talk about it twice. So we'll just kind of breeze through. And then, the last thing that, I want to talk about is because it's what most of my recent work has focused on, is one of the downsides to tacos that you maybe have thought of is that, you need this dynamic metaplastic parameter to tell you when a synapse is important, but that takes time. So what if you only have, 800 samples or 2,000 samples or 8,000 samples instead of the full data set? Can you still get that performance from metaplasticity? And the answer is not without scaling it. So originally, this approach that we have here, it's very dependent on having time to both determine when a synapse is important and then consolidate and protect that information. And this omniglot was just a very quick attempt to show that information, but it doesn't really give any more valuable insights than the other plots. So we'll just keep moving for the sake of time. And in conclusion, this is the first demonstration of a full-scale spiking network for continual learning. At the time, the only other publications that were out there were all Hebbian learning, restricted to kind of single input output layer models, or they used transfer learning and then used Hebbian learning just to train the last output layer. They didn't have, they didn't work with certain gradient learning rules for spiking neural networks. Whereas this approach, we can train multi-layer spiking neural networks. We can demonstrate state-of-the-art performance, and it's achieved, where we don't require task information, don't have to grow over time, and only train on a single epoch. So we proved our hypothesis that it was that combination of metaplasticity and synaptic consolidation, which were necessary for really getting the best effect and continual learning, and that this adaptive metaplasticity really allows for much greater plasticity than just using a global parameter, and that at the same time it can let you protect more knowledge by reaching higher states and a subset of synapses that are deemed most important. And so, as I was saying with the question, we're trying to move this to more interesting, samples and domains, reinforcement learning, other more natural images, class incremental learning. So instead of using the same output neurons per task, it has to be able to tell you what it is and from what task that, came from. Quick note, reinforcement learning always has to be domain AL because, it's just the same actions that you can take. But yeah, so that is my conclusion. Thank you. These are my references, and I would like to acknowledge the AFRL and DARPA for sponsoring and helping with different parts of this work.
Thank you so much, Nick. Anyone has questions?
I have another question. You mentioned a few. You had some references with the papers on energy efficiency. Have you looked more into that part?
No. Okay. So the energy efficient papers, most of them are the same group that was discussing event-driven random impact propagation at the time was motivating it. And then they cited a few other papers. And so it's kind of a collection of just those groups of work discussing learning on neuromorphic systems with surrogate gradient spiking networks right here. Another member of our lab, Vedant, has been doing more of the hardware-based, and actually Fatima, have been doing more of the spiking-based hardware designs. And so they've looked more into kind of the energy efficiency of different approaches and of designing, you know, the hardware for our approach and how energy efficient it can be. But I haven't looked too much into it. I focus more on the algorithm. So as you can see, you know, I came in from physics, as Dr. K said, really wanted to get into neuromorphic. And then after like half a year, I just ditched hardware completely and moved to pure algorithms almost and look at the bounce bar side. So yeah, I don't have too much to tell you about it, but we have investigated further. So sorry that I can't provide that.
Excellent. No, well, I'll look into the papers as well, but thank you so much. If you are going to investigate more, I will I will follow your work.
Right. Yeah. Oh, yeah. Our lab definitely will.
Excellent. Thank you so much. Great talk. Thanks so much.
Thank you.
There's a question on the chat, Nick. I don't know if you can read it.
Yeah, I think so. Okay. No, it does not use any delays. That's a good question. I can't, and I can tell you in the continual learning field for spiking neural networks, I have not seen anyone look at, you know, delays or delay learning to help in any form. In general, with learning for spiking neural networks, I'm not sure. Yeah, I mean, there's a lot of literature out there that I haven't covered. And, you know, I've seen some about delays, but I've never got into it because it was a level of complexity that I didn't want to introduce to my models, at least not at the time. So sorry, not to my knowledge, at least, but I can't promise.
Okay. Any other questions? If not, let's thank Nick for his presentation and stepping up in the last minute as our speaker from IMEC couldn't join us today. Thank you so much, Nick. And
no, thank you for having me.
What you've been working on. And hopefully Nick is going to defend very soon.
Hopefully.
And wish you all the best on that as well, Nick. Thank you.
Thank you. Thank you.
Thank you. Bye.
We'll see you.